I'm hoping I'm going to change some of your minds about how high ethics comes in your list there in about the next half hour or so. FICO is Fair Isaac Corporation. We're a global analytics firm. 65 or so years ago, we created the first sort of automated credit scoring system in the USA, and we simply haven't stopped since then. So half of our business today is across the globe in banking and finance, and it's mainly, I describe it as hard sums and how to implement them effectively. And my side of the business is the hard sums. So yeah, I want to talk today about transparency and ethics in our use of data and AI. I was really interested in watching Sophie's presentations, and the real challenge of being able to explain decisions and being able to make sure that people understand, you know, in Sophie's case, the forecast that she is making. So I spend a lot of my time thinking about how we make data and AI ethical. And the reason why I do that is, as well as being a consultant statistician, I'm also an ordained Church of England priest. I was a parish priest for about six years. I've been back in sort of the real world for about 10 years, but I'm constantly on that sort of interface of thinking through how we operate in our business life and how we do that with an ethical framework. And in recent years, you know, we've really begun to think about artificial intelligence, machine learning, and so on, and how useful it is. But I want to ask a question to us to start with. Is AI our friend? Well, I know I've got a friend here who thinks that she's our friend.
Alexa, I love you.
Thanks for saying I love you. You're just as sweet as pie. Know that I'll be there for you. As always, your trusty AI.
There you go. Well, there are alternative home digital entertainment resources, but they're not as good. But can we trust our little box in the corner? Can we trust that Alexa is going to make the right decisions, is going to act in our interests, that we're going to understand why she's doing the things that she's doing? You know, there's a big difference between a digital speaker and Skynet about to terminate us all. But in the middle of that are serious questions to be asked about the use of data and the use of AI. Here's an example, okay? So a company called Beauty.ai did an online beauty contest a few years ago, 2016, where they sort of trained a mathematical model to spot beautiful people, and then they scored up a whole bunch of models on whether they were or weren't beautiful. Well, guess what? Unfortunately, of the 44 winners, nearly all of them were white. Yeah. Now, that you go, well, is the algorithm racist? The chief science officer certainly said that the training sample was probably non-representative of the whole thing. But actually, you know, we've been doing with artificial intelligence, we've been doing facial recognition now for quite a bit of a time, and we've learned things. So for example, about 10 or so years ago, cameras that sort of followed your face were all the rage. And there's a wonderful example online, you can find it, of the two Target employees in the States. They've got this Logitech webcam that follows your face, and it tracks the white face of the white assistant absolutely perfectly. But when it comes to the black assistant, it can't find him. Now, is the webcam racist? Is the algorithm just biased in sort of the training set it's been built on? Or is it simply a case that it's much easier to see a white face against a myriad background than it is a black face? And it's all these kind of things that we have to consider when we're thinking about the explainability and the usefulness and the ethics of algorithms and things like machine learning. Now, one of the challenges that we have with complex algorithms is explainability. So what I've got here is a nice little chart here. On the x-axis is explainability. On the y-axis is the predictive power. So let's look at a few different ways of algorithms to make decisions and see how they rank up on that. So firstly, rule sets. So simple Boolean logic. So here we've got a calculation for someone's stroke risk. If they've got hemiplegia and they're aged over 60, we give them a stroke risk of 58.9%, and so on and so forth through there. There's about sort of 4 or 5 different decision points, and you end up in one of 4 or 5 different buckets. Now, explaining that is really easy, right? Most people, I hope, on this call can get their head around very quickly how someone falls into one of those particular 5 groups. Is it very predictive? Not really convinced it's predictive at all. It's certainly not giving me a very personalized stroke risk based on my exact age and my personal circumstances and my exercise regime or lack of it, and the stress from family and all that kind of stuff, and a COVID factor. So it's not doing any of that. Very explainable, not very predictive. Let's think about scorecards. Now, scorecards are slightly less explainable because there's quite a few more sort of variables involved, and they're sort of interacting with each other, but we can kind of understand those. So here's sort of here's a scorecard. We've got on the first column the number of times you've been delinquent in the last sort of month. We can see that, you know, the less delinquency, the better score that you have, and so on and so forth. We'll come back to this scorecard shortly. Now that's much more predictive. Combining 10 or 12 variables is much more predictive. And yes, it's slightly less explainable because you have to have a bit of a head scratch, but we can kind of see what's going on there. Let's take a jump forward. Random forest. Now, I'm not going to explain what a random forest is, but essentially, if you don't know what a random forest is, essentially imagine a decision tree and multiply it 1,000 times, okay? Highly predictive, lots of endpoints, and so lots of combinations. Can we explain it? I've got a degree in hard sums, and I'd be pushed just with pencil and paper to tell you why a random forest came to the conclusion it came to. More predictive, but way down on the explainability levels. And somewhere in between are the things that we call neural networks. These have been sort of semi-explainable for about 30 or so years. Certainly, we've got patents over in the USA on explaining this. Neural networks is a really fast developing field. I was just talking to a bank in Russia yesterday about a very recent kind of neural network that we're trying to help them to explain. We're going to go into a little bit more detail into neural networks as well to think about explainability as we move forward. But let's just explore what we mean by explainability and think about that in an ethical framework by looking at some scorecards. So look, here's an example predictive variable in a scorecard. This is the payment over your balance on your credit card. And as you might expect, if you're paying just a tiny bit of your balance, your risk is much higher than it is as you step up the bands of the payment amounts, all the way up to the top, where if you're paying more than 20% or more of your balance every month, look, we've got only 2% of all the bads in there. That gives us a really high odds ratio, a really high what we call weight of evidence, a really high score. If you look on the left-hand side there, we can represent that with that lovely chart. Nice and easy, very visual. It's easy to understand this variable by itself. Now let's think about a scorecard. We're going to bring together a few variables. Okay, so now we've not just got one variable, we've got 3 different variables. And let's take our friend Joe Bloggs here. And Joe Bloggs is applying for a limit upgrade. And this is what he scores. He's pretty good. He's never been delinquent in the last year. He's not so great on his payments. He tends to pay less than 10% of his balance back, and he did have a cash advance a month ago. Now, first thing we can do with this scorecard is that we can show what the scores are, and the scorecard is designed so that a 37 on that second column is equivalent in risk to a 37 on that third column. But clearly Joe isn't scoring top marks, and Joe wants to know why. And worst of all, my chief risk officer wants to know why Joe isn't scoring as high as he could do. Well, there's a number of ways with scorecards that we can do that. So for example, I can take each variable and I can say, okay, what's the difference between what Joe scores in that variable and the maximum possible score he could have got there? So let's try and do that. Why can he get the best score, says the chief risk officer. You've probably got one just like that. Let's look at the points lost. Well, there it is. It's that middle column there. He's lost 8 points there. That's the variable he loses the most points on. So if we want to give Joe a number one reason why he's not scoring as high as he could do, it's because he doesn't pay off as much of his credit card balance as he could do. Now, what's that got to do with ethics? Well, everything. Because firstly, I can explain this. So I can make a decision about Joe and I can justify, I can be transparent. I can declare to Joe, look, the main reason why you're not going to get the limit that you want is because you're not paying back as much as you should do. If you improved how much you paid back, we would consider you for a higher limit. That's really good. It's good for us as a company. We understand why we're making a decision. It's good for Joe as a consumer because we're helping to guide him towards good, ethical behavior. And that's why we like scorecards. Scorecards on the whole let us do this. They exhibit a number of things. We call them palatability. Okay, the palate as in my taste. When I look at a scorecard, I look at the individual components of a scorecard. It tastes good, it makes sense, right? Pay more of my balance, get a higher score. With scorecards, it's very easy to enforce monotonicity, right? So this sort of graph here, this doesn't quite make sense. If you're paying more off, you shouldn't be getting a lower score, even if that's sort of what this individual variable shows us. So it's very easy with scorecards to smooth those things out while maintaining statistical robustness and giving a fair score that is ethical. Okay, we can even engineer scorecards. So if, for example, we're in an environment that tells us that we're not allowed to penalize people over a certain age, but look, here they are on the risk. We can't directly penalize them for that. It's very easy to adjust that within our scorecard and to make other adjustments elsewhere that can help us make ethical decisions. But at the end of the day, scorecards are only so predictive. We can use them to engineer a good understanding of what's going on in the model that they are simulating, but ultimately there are better ways of making better decisions. And we've been looking at this at FICO. So for example, over in the States, if I said I worked for FICO, people would, and this literally happens to me on planes and on trains and in automobiles. I say I work for FICO and they say, oh, what's my score? And I go, I have no idea, I don't work in that part of the business. But the reason why they're asking me that is because in America, the FICO score is the bureau score, right? If you want a bureau score, it's the FICO score. And we looked at changing the bureau score from a traditional scorecard to a neural network, okay? And this is what we found, okay? We got a 2% predictive uplift on the scorecard. Now that may not seem a lot, but if you're processing hundreds of billions of scores and each of those, that little bit of uplift is worth a few dollars, that quickly becomes a massive financial boost. But more than this, and this will get all the managers really excited, to build the scorecard, it only took us 40 resource hours as opposed to 800. So straight away, using a more powerful algorithm would really help us with this model. Problem is, neural networks by themselves are essentially push a whole hoard of data into something that kind of looks like a human brain and brings everything together and looks for complex combinations and then looks for the next set of complex combinations and so on and so forth. It's really not that explainable. I mean, I'm not going to frighten the non-data scientists here, but once you're sort of, thinking about activation functions and all those kind of stuff, explaining a neural network is not as easy as explaining a scorecard. It's really not. And so whilst we might be able to make better decisions using a neural network than a scorecard. Ethically, we're going right down the tubes because we can't explain how the model gets the outcome that it gets, even if it's a better prediction. So how do we solve that? Well, let's solve it on the racing track. So I'd like to say I'm a big fan of driving cars. Our chief analytics officer, Scott Zoldi, loves racing cars. So he loves this example. I've got a convertible Mercedes, but I think that's more a midlife crisis than a love of speed. But anyway, let's think about driving a car, okay, and coming up to a corner. Now, I don't know if you've ever thought about what you do as you come up to a corner and turn it, but please don't, when the next time that you're doing it, stop to think about it, because your brain is doing all of this automatically. But as you come up to a corner, essentially you're on full throttle, and then you move from acceleration down to braking, and so at some point you're then going to change the gear, and then you're going to start to turn into the corner, and then there's a sort of a balance between the throttle and what we call trail braking. There's this wonderful thing called late apex, and then we are out of the corner in full throttle. Now, if I have a perfect clean racetrack and a perfect car and a driver who I know the exact weight of, their exact mood and so on, I can model that mathematically beautifully, and I can tell you exactly when to do each of those things and how much to brake and what speed and when to put the throttle on and so on. But life isn't that easy, okay? Think about stopping a car, right? We've all done a driving test. We've all been asked what our stopping distance is. The stopping distance is a piece of fiction because it changes depending on the circumstances, right? So it depends upon how fast you're going, depends upon what the temperature of the road is there water on the road, and all of these things combine together to make the stopping distance calculation actually really, really complex. But really, really complex problems are handled really, really well by neural networks. So let's look at how a neural network solves that kind of problem, okay? So we have these latent features, and they are the combination of all the data. And essentially, this is very much a dummy's guide. The first latent feature looks at the top combination of all those data and how that varies to make a prediction. And then the second latent feature does that again based on what the first latent feature is, and so on and so forth, and feeds it all in. That's a very dummy's guide. So if you're a neural networks expert, don't write to me afterwards and tell me that I got it wrong, because I did. I'm just trying to help us understand this for those of us who, when they say, can you build me a model, we go, I have people to do that. So think about that. What are the latent features explaining to us? Well, the latent features explain to us all these kind of combinations. So for example, the combination of road temperature, air temperature, and water is going to tell us whether there's ice on the road, right? The speed and the variability might tell us if the technical nature of the car. We want to think about how all the different elements of the car, the brakes, speed and age and all these kind of things are coming all together. And crucially, when we build this model to predict the braking distance, ultimately we need it to be explainable. We need to understand how it's got to the decision before it actually makes a prediction. And these latent features help us to explain those complex interactions. How do we draw them out of the model? Okay, so let's go back to our neural network. Now this time, let's build a collections scorecard, okay? So I'm trying to predict how much these people are going to cost me to recover their debts. I've got all these information, the value of their collections, and if they've been delinquent before, and all that kind of stuff. So here's our first neural network, okay? And you see it's very complex. I've got lots of data coming into each of these latent features. Each of these latent features is combinations of lots and lots of data. And I get a great output, but I can't explain it. I can't explain how we got the score at the end. Now, let's take away a few of those inputs. Even though this is a better prediction, let's take away a few of those inputs, because otherwise I'm going to be left like this lady here. Okay? Let's take away some of those inputs. So now my latent features are only a combination of 2 or 3 variables rather than lots of variables. Suddenly, if I look at those latent features, I can explain it better. And look, what I can even do, for example, is go, well, I've been left with another, there's my third latent feature there. It's still got 4 inputs. Let's dissect that and let's put 2 new nodes in that basically take all the inputs and subdivide them into different inputs that then go into that input. And now I can begin to explain those. Now, explaining the complex interaction of 6, 10, 20 variables, very difficult. Explaining the interaction of 1 or 2 variables, much, much easier. Now, again, this is all very, very simplified. In practice, is a little bit more complex. But in doing this, we can make neural networks much more understandable, okay? And that means that we can explain the latent features within a neural network. And that means we can justify the decisions that we are making. And that is really powerful. It's ethical, okay? Now, so there's my lovely thing. I wanted to move us forward very quickly because we're running out of time. I want to show as an example of how bias creeps into algorithms and how we can spot it. Okay, so we all live in highly regulated environments, whether we're in the US, the EU, the UK, and those environments tell us that we must make decisions based upon bias. Now, there's a very famous example of this. This is the Compass model in the USA used by a particular county to predict whether people who are coming out of jail would recommit a crime. Okay, and what they found was that the model was built on a test set, had a high prediction, and then it failed magnificently in real life. And it had a classification error on African Americans of 45%. What that means in real terms is that for every second African American coming out of prison, it made the wrong decision about whether they would or wouldn't commit another crime. Now, if you're going to put parole conditions on people based on your model, that is a huge, massive failure. Why did it do that? Okay, well, I'm going to show you. So on the left-hand side here, you've got a simple 2-variable chart. You've got on the x-axis the safety of the neighborhood measured by how much crime happens in the neighborhood, and on the y-axis you've got the income group, so basically how wealthy people are. Okay, and you can see on the green the density of people tend to live in higher income areas which have less crime, and that's sort of a correlation as you go through. Yeah, if you live in a low crime area, it tends to be a high income area, and conversely, and that's the general population. And what's interesting is when you therefore look at the recidivism rate of people coming out of prison, depending on where they live, and look at the crime rates there and the income rates there, lo and behold, the people in the top right hand corner are very low recidivism rates. The people in the bottom left-hand corner, those high crime areas, low income areas, very high rates. Right, we got that in our heads. The thing is, when you look at the 3 different sort of racial groups in this county in America, broadly called white, black, and Hispanic, and to see where they lived, you see something very interesting. Most white people follow that overall population correlation, right? If they live in a higher income area, it tends to have lower crime. If they have a higher income, they tend to live in a lower crime area. But when you look at people who identified as black, that didn't happen. Even though they had higher incomes, they tended still to live in higher crime areas, and higher crime areas is correlated with recidivism in the overall population. So think about how the model that you've built in the second chart then interposes on those individual populations. The model is telling us that if you are in that combination, you are less likely to commit another crime. And for white people, that kind of works. But if you're black, the chances of you living in a combination of a low crime area and having high income are negligible. It's not because you don't have a high income, it's because high income black people in this area of the USA still tend to live in low crime areas. And so if your model is built around low recidivism is in that top right hand corner, black people are simply never going to fall into that corner, even if their recidivism rates as their income increases goes down. 4% of blacks were wealthy and in safe neighborhoods as compared to 30%. And simply ignoring the fact that for various historical reasons, different racial groups lived in different areas led to a completely biased model. And that's incredibly dangerous. So the lesson from that is that if you explore your data, if you sort of take your model and dive into the combinations in the model and look at things like that, you can spot that. This would have been really easy for a data scientist to spot if they'd gone, right, press the button, got the model, and not just gone, there's your model, use it, but gone, hang on a minute, let's look at this and let's think about it from a bias perspective. So do not be blind to bias. You can use incredibly complex algorithms, but you need to be able to find the relationships inside them and test those combinations, those latent features, those combinations of variables for bias in your subpopulations. That means that producing a model is not just a business decision, it's a moral decision as well, right? And this comes even down to a simple loans origination scorecard. When you implement your loans origination scorecard, it is not just a business decision, it is a moral decision to use the algorithm that you have. Are you absolutely sure that you are not introducing bias into the system that will detrimentally affect some people? And you know what, even with complex models like neural networks, we can go into those latent features and show what they're doing in subpopulations. We can see there's bias. We can take machine learning boosted trees and dissect individual scores. What we can even do with machine learning models these days is that we can go into an individual person, look at an individual variable, even in a complex model, and say, okay, so this person had a higher FICO score, it wouldn't really affect their score overall, but we can see if they had a bit of the lower score, they wouldn't. Now, in credit, that's an interesting idea. Think about medical adherence scores. I'm building a model to see whether somebody will take their anti-stroke medication or not. Right? If the model tells me that if they were 5 years younger, they would have a better outcome, I can't say to them, please come back to me when you're 5 years younger. But if the model tells me that if they did 15 minutes more exercise a day, that they would have a much better outcome, then I can think about incentivizing them on that. So I can say to them, look, I'll give you a smartwatch as long as you hook it up to the insurance app, so I can see how many steps you're doing a day. If you stay above 7,500 steps a day, I'll bring your insurance premium down. And now we're using AI, complex models, explainable complex models, to make ethical decisions, not just for us as the institution, but for our customers. We're making a better decision for ourselves because it's more risk intuitive, and we're helping our customers to make better decisions and to incentivize them to do that. So let's bring that all together. I've kind of gone a sweeping journey through sort of AI and ethics, but I've done it for a purpose, to help you understand that as we increase complexity, we can actually bring explainability up with us. And in doing so, we can address some of the real ethical issues in complex algorithmic modeling, that when we have algorithms, mathematical models that have complex interactions, we need to be able to understand what they are doing in order to properly use our models. So I want to say to you, if you want to be ethical in your use of data and AI, firstly, be explainable first and predictable second. Second, actively enforce things like palatability, monotonicity. They help to address biases. There are ways to use complex algorithms and yet explain them. And finally, do look at your models, at your complex models, look at the latent features, look at the combinations of variables, check for bias. It will stand you good in the front end. Thank you.